Hi, that's not right. Hi, I'm Jamie. I'm from DeepMind. I'm talking on behalf of myself, Borja, who a colleague at DeepMind, and Giovanni, who is at the Turing Institute and is now at MSR. And I'm going to talk to you about reconstructing training data with informed adversaries. Okay, so our work is focused on understanding the kind of privacy leakage that can occur when machine learning models are trained on potentially sensitive data. So specifically, we're going to consider a supervised learning setting represented by this setup here that I've depicted here. So we're going to assume that the model developer has a training set, and we're going to just segment it into two parts. One part is going to be, we're going to call the fixed part of the training set, and that's going to contain n minus one of the training samples, and then we're going to have an additional sample that's depicted here by a picture of my colleague Borja. And this data set is going to be ingested by some learning algorithm represented by this box A. And you can think of this algorithm as like SGD or something like that with your favorite choice of learning rate or batch size and things like that. So after this learning process is completed, it's going to spit out some model parameters. So I'm going to call these model parameters the release model by the model developer, and this is represented by this box, this theta box in green. Okay, so given that process, we can ask what kind of training data privacy violations can occur. And the most commonly studied privacy attack in machine learning is probably, I think it's fair to say, is membership inference. And in membership inference, the adversary gets given this theta in green, and it gets given a record. And given these two pieces of information, and potentially some other side information, the goal of the adversary is really to output a single bit, basically just to decide if this record was a member of the training set or not. So instead in this work, what we wanted to do was remove this assumption that the adversary already has access to this record and say, given access to these model parameters and potentially some other side information, can the adversary reconstruct the training data record? And so we want to do this for a few reasons, but I'll give two very briefly. So the first is, if you think about the amount of information that is leaked by a privacy attack, membership inference really relies on one end of the spectrum. It represents a single bit of information that the adversary can learn, namely if this record was a member of the training set or not. While on the other end of the spectrum, you have reconstruction attacks, and they really represent the maximum amount of information that an adversary could learn about a training point. The other reason is that membership inference attacks necessitate that the adversary already has access to a record from which they want to learn if it's a member or not. And already having access to a record can represent like a privacy violation in a lot of cases. So for example, belonging to a social network is usually public information. So the fact that I belong to a certain social network isn't really a privacy violation. However, if an adversary was to collect my private information from that social network or get my private photos, I would probably be quite upset about that. Okay, so informed adversary, what does that mean? It's in the title of the paper. Well, we call our adversary informed because we're going to assume the adversary has a lot of knowledge, like an unrealistic amount of knowledge. So we're going to assume that it has access to all of the training pipeline apart from the point Z that it wants to reconstruct. So let's enumerate what it knows. It knows the model parameters that are output by the model developer. It knows the algorithm that the model developer used. So it knows that SGD was used with a particular choice of learning grade for a number of epochs. It also knows all of the fixed part of the training data set. So it knows all of the training data set apart from the single point that it wants to reconstruct. And we're also going to give access to some kind of prior distribution from which the training data came from. So we're going to allow the access to sample from this prior distribution. Okay, so given that, how do you actually instantiate an attack? So it works in 4 phases. The first phase is, as I've already described, the model developer comes along, trains on some data set and spits out some model parameters. This model can be any kind of parametric model, but for all of our experiments, we're just going to consider very small, simple neural networks like CNNs or MLPs. Okay, so the first part of the actual attack goes as follows. The adversary has access to a prior from which it can sample from. So what it's going to do is it's going to sample n times from this prior to get n new models, because it knows the algorithm that was used, it knows the fixed part of the data set, the trained data set, so it can essentially create n different copies of this release model by the model developer, where each of these models are only going to differ by a single training point. So now it's done that, so it has collections of pairings of model parameters and training points that were used to create these models. And so all it wants to do is learn a mapping between model parameters and training points. And so we can just construct this as a supervised learning task again. So we're going to just throw this into some kind of learning algorithm, like SGD or something like that, and learn how to go from model parameters to training points. And this is going to output another model. We can call this the attack model, represented by this phi in purple. And if this learning task is successful, then the algorithm will have learned how to reconstruct points from these models. And so the final phase of the attack is just to apply this to the model trained by the model developer. Okay, so I don't have time to probably go into the experimental details too much, but the too long didn't read really is that using an attack, as I've described here, the attack works very well on these kind of fruit fly data sets of the vision community, so MNIST and CFAR10. So what I'm plotting here is columns of original images and then reconstructions of those images for the MNIST test set and then the CFAR10 test set. And you can see that most of the time these reconstructions look almost identical to the original counterparts. Okay, so getting a bit more into the weeds of what worked well in the attack, or maybe the more interesting findings. So the first thing that we thought was interesting is that these reconstruction attacks are possible even when there is randomness introduced by kind of mini-batch SDG. So even when the model developer uses SGD, we're still able to do reconstruction. So even when specifically there is randomness introduced into the adversary attack pipeline that they can't explicitly control, these reconstruction attacks still work. So what I'm plotting here is a plot of the reconstruction error, the average reconstruction error over the MNIST test set against the batch size that was used by the model developer. And this red line, this horizontal red line, represents a marker for when reconstructions become practically indistinguishable from their target counterparts. So anything that sits below this line represents a very, very good reconstruction. And yeah, this line goes down, and it goes down because essentially as you increase the batch size, you reduce the amount of randomness in the training pipeline, so you increase the determinism, it becomes more deterministic, and so it's easier for the attacker to learn the mapping between model parameters and training points. Yeah, however, even at a batch size of 2 to the 8, so a relatively small batch size for an MNIST classifier, we can still do a very good reconstruction attack. The second point is that reconstruction isn't a byproduct of overfitting. So it's not the case that we only can reconstruct against models that have classically strongly memorized the training points. So for example, all of our experiments are on models like MNIST models and CFAR10 models that have a difference of training and test accuracy that only differ by a few percent. So yeah, this is an example of that, an MNIST classifier that only differs by 1% between training and test accuracy, and the reconstructions look almost identical. Next, most of our experiments are operating in a white box setting, which means we assume the adversary has access to the internal model parameters of the model trained by the model developer. However, if we remove that assumption and we only allow the adversary to have access to the outputs of these release models, so we assume the adversary only has black box access, the attacks work essentially equally as well. So we don't really need this assumption. Next, it's easier to reconstruct against larger models. So if there is enough information, there are enough parameters in the release model to store information about your training points, then these reconstruction attacks become possible. So Here's an example of that. There's a release model that only had about 800 parameters, and the reconstruction doesn't look great, although we are leaking the label. And then if you increase the number of parameters by times 10, you've increased, like, the reconstructions become very good. And finally, these reconstructions are very stable under various choices of learning hyperparameters. So the choice of, like, optimizer or learning rate or things like that don't really affect these reconstructions. Okay, so what works less well? So that was the good stuff. Here's the bad stuff. Touched on two failure modes of the attack. One is our attack seems to perform less well when we don't know the initial parameters of the released model. So if you think about it, like, the adversary has access to the final parameters of the released model, and if it has access to the initial parameters of the released model, essentially all it needs to do is learn the data that caused this trajectory from initial to final parameters. And so if you remove the assumption that the adversary knows the initial parameters, there is randomness introduced into the attacker's pipeline, and this basically makes the attack much harder. So this is an example of that. The second failure mode is when you have relu activations, which is kind of a shame, because rel activations are a very popular choice for vision classifiers. So our attack works very well against smooth activations, but essentially fails or performs less well when we had relu activations. So that's work in progress to fix that. Okay, so turning our attention to defenses. Our threat model is designed specifically with a very, very strong adversary. And we did this intentionally because we wanted to try and mimic the adversary that is considered in the DP threat model. The differential privacy threat model specifically guards against membership inference. And membership inference is a strictly easier problem than reconstruction attacks. So the question really shouldn't be, does differential privacy protect against reconstruction? It's really how much differential privacy is necessary to protect against reconstruction. And so the rule of thumb for DP training, really, to protect against membership inference attacks is to have a very small epsilon, so privacy budget. But this usually comes at the expense of accuracy, right? So to have a small epsilon, you have to add a lot of noise to your training process, and this in turn gives you a kind of a hit in test accuracy. So the question is, like, if we're willing to be vulnerable to membership attacks, but we specifically want to guard against reconstruction, can we get away with larger privacy budgets? And without going too much into the theory, we have some results that state that if you train your model with epsilon differential privacy or like variants like RenUDP, then the probability that you can get a good reconstruction after the adversary has observed the model is bounded above by e to the epsilon times the probability of a good reconstruction even before observing the release model. And so this probability you can think of as a prior probability of the ability to reconstruct over the data distribution. And so, like, for a simple prior, for example, like a uniform prior over a d-dimensional sphere, we can show that this dimensionality term appears in this prior probability. And so the kind of epsilons that you would need to protect against reconstruction attacks are of the order of the dimensionality of the data. And we also have some empirical evidence on non-toy data sets like MNIST and things like that show this insight also holds there. So this is what I'm plotting at the bottom. Essentially, for different epsilons, the reconstruction, and on the bottom right is the target. And so you can see that these reconstructions only become similar to the target after about epsilon equals 1,000, which is approximately the dimensionality of the data of the MNIST data points. If we're willing to be vulnerable to membership, we specifically want to guard against reconstruction, there is some preliminary evidence that shows we might be able to get away with larger privacy budgets. Okay, and just to quickly wrap up, reconstruction attacks enable us to understand the maximum amount of information that could be leaked about your training data set. So if that's what you care about, you should consider reconstruction attacks. We have attacks that are feasible on both convex and non-convex models, so they walk across a broad spectrum of machine learning models. There's a lot of specific details that you need to get right to make these attacks work. So specifically scaling them to models that achieve SOTA on different learning tasks is still work in progress. mitigating reconstructions can be easier than mitigating membership inference, as long as your uncertainty in this prior is large enough, in this prior probability. And the really nice thing about the way that we analyze reconstruction is that modeling your vulnerability to reconstruction attacks really boils down to modeling your prior probability of reconstruction. And so if you can kind of understand that, you can understand how vulnerable you will be to reconstruction attacks. And with that, happy to take any questions if there's time.
So we have plenty of time for questions.
Yeah,
Thank
I
you.
have a quick one. So in order to understand the cost of this attack, so how many samples do you need to build, and how many models do you build, even for the simple ones?
That depends on the data set. For MNIST, you can generate a reasonably good reconstruction attack when you sample about 100 points. For CFAR, it scales a bit larger, so you'd probably need like in the order of thousands. So it's a very costly attack.
So, and you need to build the model from scratch, or you can do some transfer learning or something?
You can do transfer learning. We have experiments that show you can do transfer learning. But it's still a very expensive attack. It's not like a realistic attack.
So in order to scale to very big models, it will take years maybe to run some of this attack. Is that correct?
Using the attack as like defined here, it probably wouldn't be feasible to scale to larger models, but yeah, that's a work in progress. So, but yeah, using the attack as is now, I don't think it would be able to scale to large models.
Hi, Mingxun Zhou from CMU. So I wonder why even a very, very large epsilon can protect from reconstruction, because in the DP definition, basically the epsilon correspond to e to the epsilon in the privacy definition. So I wonder why. So for example, e to the epsilon, and when the epsilon is like 1,000, then basically e to the epsilon is like very, very huge, right?
Yeah, it's a good question. I'm not sure if I can just like intuitively describe it. Essentially, it really just boils down to the amount of uncertainty you have in your prior. So if you think about DP as a kind of prior over a posterior thing, then if you have enough uncertainty in your prior, then and you train with DP, you can basically ensure that your posterior will have enough uncertainty in it, or remaining uncertainty in it. But I don't know if I can give you a more intuitive answer than that.
Oh, so basically the epsilon here is something like using a group privacy to get that 1,000, or?
There's nothing to do with group privacy here. It's basically just saying that if you're willing to be vulnerable to like simple attacks that leak like a little bit of information, then you can have epsilons that are larger than like 10 or 20. You can like have a reasonably large epsilon if you're willing to like leak a small amount of information.
Okay, thank you.
Thank you. Oh yeah, hello. Can I have a mic here working? Okay. I'll just be loud enough. I was gonna ask. So you showed us the experiments with image data or tabular.
Yeah, really good question.
Sorry, not like construction. Yes.
Really, I mean, there is work out there already, like the work from like the Brain Group on using like leaking data from large language models. So like the attack that we've described is quite specific to vision and classification, but I don't see like any kind of fundamental reason why these kinds of attacks couldn't be like applied to other kind of modes of data.
Cool. Oh, it's working. Yeah, okay. One more quick question. What if the member of the point was repeated multiple times? Like, for example, in MNIST, right, the digits are kind of looking similar. Like, does that affect how?
Times. I mean, it probably would affect it. It'd probably make it easier. But yeah, I mean, the attack would still work. It just like maybe the kind of threat model would had to be changed a little bit.
Yep. Cool. Thank you very much. Let's thank Jamie once more.